Okay, good morning, everyone. I'm very pleased, let alone honored to be here today. I knew it would have been exciting. It is even more exciting than I thought. So thank you so much, Lydéric, for this invitation. And thank you all, actually, because I'm really enjoying my time. So today I'm going to talk, I'm going to share a few thoughts regarding some techniques that we have been developing over the last few years in the course of my ERC. And as you will see, I'm out of scale because my ERC was entirely micro to meso. So I'm definitely sitting on the left side of Lydéric droplet, and the task today is figure out ways of moving on the right-hand side of the droplet. It's not obvious that this can be done, but I am rather confident, and that's what I would like to discuss with you and after the workshop, of course. Too much. I will just give you a few ideas on what the project was about the method, and then I think I will skip the central part of my talk and rather try to converge on the topic which is on stage today, namely how to use these techniques, mesoscale techniques, to try to make a contribution to the quantum nanofluidics issue. So, in the beginning, as I said, this was the project. The project was about soft flowing matter. I don't think I need to tell you much about this. To me, soft matter is very fascinating because it's a sort of quantum entanglement between liquid, gas, and solids. And when you compose them together, Newton plus Newton doesn't make Newton again because the configurational degrees of freedom change completely the rheology of your soft material, be it foam or emulsions. To me, it was interesting in many respects, not least the fact that, numerically speaking, when you have droplet formation within a microflow, highly confined microflow, it's a tough computational problem because you have a moving interface which is deforming dynamically and so on and so forth. But I mean, it is interesting, I would say, under any angle, I would say. So basically, the idea was just to see what we can contribute to the understanding of these new states of matter, and in a sort of jesting mode. I should be embarrassed here because I heard a lot of chemical details, but we were interested in replacing molecules with droplets, which of course is a sort of provoking statement. The question being, nevertheless, and this is serious, what can we think in terms of new materials based on the non-equilibrium assembly properties of droplets? So there is zero chemical specificity, and again, I apologize. But eventually, the task of going to micro to nano is precisely this. I try to reinsert the amount of chemical specificity, the minimum amount which is needed in order to somehow to capture the relevant physics. In any case, in the beginning, and I'm talking 5 years ago, the question was, how do we describe numerically multi-droplet configuration under strong underflow to begin with and under strongly confined flow. I think you can easily imagine that it's very hard to do quantitative analytical work under these circumstances. So that was the main aim of the project. And again, why? Again, here, I think you know far better than I do, but I was captured by this picture a while ago, where, in fact, this is work by Roma and Marmottan, and they show that somehow there is a sort of analog of condensed matter using droplets. This is a dilute flow. This is water. It's an oil jet, and the oil jet is squeezed by water jets up and down, and so you break up, and depending on the ratio between the oil mass flow and the water mass flow, you generate either dilute states, these are small droplets, which would be the analog of a dilute gas, and they tell me, by just adjusting, changing this order parameter, namely the ratio of the two mass fluxes, you can go from, sort of disordered, this remains quote-unquote a liquid, and then you keep pushing, you keep increasing the mass flow of oil, and you go toward a steady state with hexagonal symmetry. Then there is a switch from hexagonal to sort of honeycomb, and then in the end you end up with a sort of plug flow. So there are a sort of structural transition, and again, the experimentalists tell me that this is beautiful because this is very controllable from the experimental point of view. So just by regulating this ratio and the pressure, you can move from a gas to a sort of moving solid. And the rheology is absolutely fascinating. The rheology, of course, is nonlinear, and for instance, here you have, this is basically how much flow you can move across the microchannel as a function of the pressure you apply. And there is a first branch, B1, which is nonlinear, and these are basically the droplet configuration associated with the different spots in this branch. So you keep pushing, you get more and more flow. After a while, there is no way, even if you increase the pressure, there is no way you can drive more flow than this. And that's because there is a structural arrangement from the honeycomb topology to the one-dimensional topology, and this is a crisis. And after the crisis, then the multi-droplet configuration can start to flow again. And of course, this is oil and water. They are both Newtonian, but their combination is all but Newtonian. So can we capture this kind of complexity? Yes, I would say in hindsight, we were, I would say, surprisingly successful. I think it's a luck strike and something I would like to, in fact, discuss with you. But just to fix the ideas, there are many actors on stage. But by far, the most dominant ones are capillary forces. Of course, this is microfluidics, surface tension over the diameter square of the droplet, and we are talking droplet of the order of 100 microns, so we are definitely microfluidics. The part which connects, I think, with today is what we call near contact, which almost derivatively means nothing, except the fact that these are the forces which are supposed to take stage when two droplets come close together. Close means 10 nanometers. I mean, it's slightly supramolecular, but it's definitely a distance between two droplets is much smaller than the droplet's radius or diameter. And confinement is definitely there, as you can see from this picture. This picture is realistic. There are basically 2 rows of droplet flowing, maybe 3. So the confinement parameter, which is the diameter of a droplet versus I should have called W, is the width of the channel. We are in the order 1, order maybe 0.2, 0.5, but certainly it's not a small number. And of course you have the capillary number. The Reynolds number is not particularly relevant because these are slow flows. And this number, I don't remember the name of what this means, but it measures basically the deformability, which is another ingredient which would be very hard to describe other than by numerics. And of course, Lydéric did a lot of work in this direction. I remember his beautiful paper where he introduced the fluidity, which is the inverse of the viscosity, which is non-local. I mean, there is a lot of beautiful work, both experimentally and theoretically. But again, the point for us was, how do we describe this type of configuration, which are dense, confined, and deformable? And they span, nevertheless, 6 decades, because the promise of the ERC, the only reason, I guess, why we got the ERC is because we promised that we would go all the way up to the experimental scale, meaning 10 nanos to 1 centimeter, maybe 1 millimeter. And honestly, these are 6 space decades, and there is no way you can basically describe 6 decades with a single method or with a single code, unless you torture yourself with very, very, I would say, aggressive grid refinement techniques, but this is a big, big pain in the neck. So the question was, again, how do we take into account these complexities over a spectrum covering 6 decades? And of course, whenever you cannot simulate, what do? You coarse grain. And the theoretical question was, how do we coarse grain what we call near contact interaction, okay? And, okay, if you have, I would say an exascale computer would not be enough, but suppose it is enough, then you can do all the way, all simulation. If you have a small computer, you have to use much more brainware and try to figure out what a sensible coarse graining would be. The problem is density. Just to give you, again, an idea of the scales, the black box is basically the delta which you can afford given your computer, okay? If I want to resolve the near contact interaction, the thin film between the two droplets, I better go to 10 nanometers. But if I make myself 10 nanometers, I cannot describe the entire device because it's 1 millimeter, and 6 decays, no way. So what we did is embarrassingly simple. Okay, just on dimensional ground, we know that there must be some interaction between the two interfaces. Here we leave the exponent free, but dimensionally, unless you have anomalies, the exponent should be 4, right, by dimension, and A should be related to KT. So by doing that, we use basically a delta. Instead of being 1 nanometer to resolve actually these forces, we basically use delta around 1 micron, meaning that we are coarse graining basically 2 to 3 orders of magnitude in space, which is pretty audacious, I would say. And usually you don't expect to be forgiven for doing so much coarse graining. I can anticipate the bottom line. We have been consistently forgiven. I don't know exactly why. I suspect that unlike turbulence, where every scale is coupled, the problem with turbulence is not that the spectrum is broad. Yes, this is a problem. But worse than that is the spectrum is continuum. So you cannot isolate. There is no scale separation whatsoever. For some reason that I do not understand, seems to me that the near contact interactions are decoupled somehow from the global rheology. At least that is what I conclude out of our experiment. So just to say that we did an outrageous amount of coarse graining, and in the end I should be ashamed, all we did was to complement the lattice boson with these extra terms. I don't discuss deformability, which is, by the way, a very beautiful topic on its own. Methods, well, yes, I've been dealing with lattice Boltzmann for a long time. My wife always blames the fact that I know Boltzmann much long, since she knows me, and she knows me for a long time, she has heard about Boltzmann, say, what boring. I return that with lattice Boltzmann we have been playing around in many, many different applications, so I still enjoy it very much, and I hope that today there will be new application to come. Just for those who never heard about it, it's an interesting method to actually cheat on continuum mechanics and replace molecules with pseudomolecules which move on a highway. Literally, this is not a cartoon. That's what you do when you run a lattice Boltzmann application as we speak. You freeze the molecules along, as you can see, 18 directions. Center of the lattice to the center of the faces, center to the edges. And if you are virtuous, you would also include the vertices. We don't, but it would be better. And the main point is here. Apparently, this looks like a suicide because we are interested in fluid dynamic problems where the quantities depend on space and time. And in Boltzmann kinetic theory, of course, you have the molecular degrees of freedom. So you solve a problem in 6+1 when your physics is in 3+1. And I promise, for nearly 10 years, we would get the question, are you really solving Navier-Stokes? People didn't want to believe that. And I can sympathize with that. Nevertheless, it so happens that if you choose this discrete velocity cleverly, with enough symmetry, you can just exactly reproduce the Navier-Stokes equation. It's not an approximation. You just get the Navier-Stokes equation. It will be a long story, but let me tell you in a nutshell the secret. The secret is that since you work in an extra dimension, because the velocity is an independent, this is phase space, v is independent of x, you always move information along straight lines, no matter how complex your flow, no matter whether your foam is going crazy, whether you have a turbulent flow, the information always travels along straight lines. Believe it or not, this is a magic property. It allows you to describe complex geometries, like cars, engineering design, while keeping parallel performance always up to shape. I mean, you have to do hard work, but lattice Boltzmann works consistently extremely well on parallel computers, any kind of architecture. And there is more to that. That would be too long. But the second point I want to make, forget about this equation. That doesn't really matter. The second point, nevertheless, is that when the molecules, the particles move from one lattice size to another, this is the streaming motion, molecular motion. This is exact on a computer. If I'm a right mover, and when the clock comes, I just move right, blind. This comes from cellular automata, Frisch's, Lacker, Pommeau, a lot of work done in Paris. And this expression, this is just a memory shift, so there is no floating point errors in this simulation. That's also a major problem. Collision are relaxation, and most importantly, if you have external forces, and that's really crucial to what we are discussing today. External forces could be as simple as gravity, but could be forces which depend on the density configuration of the fluid, density functional theory. Basically, they enter the scheme by biasing. If I have, for instance, a wind blowing in this direction, there will be a bias for the population which go with the flow. And there will be a penalty for the population which move against the flow. This penalty is a bias term as sub I, and that's how, for instance, you describe phase transition. How droplets emerge from a fluid simulation is just because of this extra bias, and that is basically how we do complex fluids, how we do soft matter. It's basically a few 20 extra lines of code. And that's also remarkable. I mean, the simplicity of the method is remarkable in terms of you can open up a Pandora box of complexity just by adding a few extra lines of code. And this is an example that it works. This is a recent simulation we did. That will be another talk. We computed the flow inside or across a sponge and discovered that there is a beautiful synergy between the structure of the sponge. This guy lives minus 500 in the sea, and the question is how do this sponge manage to live? There is a beautiful synergy between structure property and hydrodynamics, but again, that's another talk, but these are the numbers, 50 billion size, 5 petaflops. That's an example where lattice boson does its best in terms of paracomputing. Now, back to droplets. Again, skip the math, but the point is that we can code this bias term I was mentioning before in terms of density functional theory, okay? And by doing that, you inject into your lattice boson scheme non-ideal, of course, interactions, so non-ideal equation of state. You can control the surface tension, and you can control the disjoining pressure, which is pretty close relative to the near contact interaction I was discussing before. So there is really a lot of richness. I mean, you have to go through the details, but in the end, in the code, what you do, basically, you add some sort of lattice potential, very simple, which encode the potential energy interaction. And this is a sort of philosophical, but I think it's important. It's a sort of paradox. We are using lattice Boltzmann, which is a derivative of Boltzmann, and many people think, well, since you are a derivative of Boltzmann, you cannot go beyond dilute gas. No. It's very different. We are using model Boltzmann equation called Batnagar, Gross, and Crook, 1954. And in this model equation, paradoxically, they are more general than the equation they derive from, because, as I said before, you can code your equilibrium based on the physics you want to implement, and you can code your external forces based on the physics you can implement. And if I code up for density functional theory, I'm implicitly describing a dense fluid. Now, being rigorous from the point of view of statistical mechanics is another story. You have to be very cautious, very aware that what you're doing is a sort of empirical coarse graining, but nevertheless, this allows you to explore situations of enormous complexity with a simple computational tool. So, near contact interaction, there is not much I should add. When we started the project, there was no lattice Boltzmann that would be able to keep the droplets separate, not under the condition of microfluidic experiment. The droplet would consistently merge and coalesce. It took to us about 4 months, and the credit goes to Andrea Montessori, and he found a way of implementing this near contact interaction. And ever since, and that's where the lucky part, no matter what kind of application we have been facing, and I'm not going through at all through this list, we investigated, I would say, almost 10 different states of soft-flowing matter, and the code always worked, basically, which is, that never happened in my life. Normally, when you change your application, something crashes, you investigate, you fix it, and then you go again. This went very seamlessly, and that's why I'm kind of optimistic that maybe we can export that to the nano, but we'll see. So just as an example, as you know, in fluid dynamics, there are more dimensionless numbers than physical phenomena. So here we didn't want to invent any new number. We call it just n for number. And this is the ratio of the near contact interactions versus the capillary forces. And just as a test, we wanted to know how far we can push our flow. This is a flowing crystal. Before the crystal basically gets broken, it becomes disordered, and eventually it melts down. And we just discovered, not much of a surprise, if n is 0 means that you have no repulsive near-contact interaction, so you coalesce. And basically, you can keep the crystal alive, meaning flowing and regular, up to about 0.1. And if you go beyond 1, then you generate a disordered emulsions, which is interesting, of course. And that would be, of course, another application. Here, for instance, you can tune the connectivity by changing the aperture angle. This is the single file droplet flow, and then you open up the channel, and of course you generate this kind of complexity. We did some very dense, this is 0.9 volume fraction, interesting phenomenon. Instead of going through the bulk, you see that the droplets behave like humans, like pedestrians. I don't have the movie on me, but they would move sideways. There are other interesting phenomena, droplets which go up and down, they serve as a sort of active pump. Just a lot of interesting phenomena, but I don't want to, active matter, again, would be another. How much time do we have, Lydéric? Because I would really like to focus on 10 minutes, 5 minutes? Okay. So mesocoupling to QN, quantum nano, this is new. This could be rubbish, but when I read in one of Lydéric paper, the emergent interface between hydrodynamics, electrodynamics, condensed matter is an uncharted territory back for further exploration, I just could not resist. We have to do something here. So how can we contribute? I don't know, you'll tell me. But I'm in love, of course, with quantum friction. This has been discussed before, so I don't need to repeat myself. Then I concocted this sort of diagram, which appeals to me from a theoretical point of view. So as I understand, you guys have 3 species, hadrons, electrons, and phonons. And there is a very rich diagram because the energy and the momentum can flow both ways. And I never really engaged myself with Keldysh, but I know the formalism. I like it, but I never tried, and it's good like this. So to me, your paper is a beautiful box where you enter the non-equilibrium quantum many-body, but in the end, and please correct me if I'm wrong, you provide a result which looks pretty classical, because you provide essentially friction coefficients, and you provide expression that, again, if I read it correctly, they are basically linear. The force, the frictional force is a coefficient. The coefficient is subtle, contains a lot of physics, times the relative velocity. And honestly, if this is true, double F, I think we are in business. And I totally forgot that back then, this I already explained, I should be ashamed. I even signed that paper, but I'm a very ancillary author. The group is Vesitis in Harvard. They had some experiment where they had graphene oxide. You are the expert. Don't ask questions on this, please. I would feel very embarrassed. But the question was, they have this sort of how would I say, molecules anchored to the walls of the graphene, and they wanted to know, they had different setups, experimental setups, and they wanted to know, in the end, what is the permeability of the device. And this was perfect for our purposes. So what we did, we just postulated something like this, that there is a friction, y is the coordinate out of the wall, Okay, so it's a heterogeneous friction, exponential. Exponential came from the experimental advice, times the velocity. This is the fluid velocity in the flow. Please do appreciate that this is very different from the collective way a fluid dissipates energy, namely through viscosity. Viscosity is scale selective. Viscosity is nu k squared. K is the wave number, meaning that the small structures are dissipated and the large structures don't feel much dissipation. This is a very different form. I'm not even sure it's rigorously well justified because this is an individual form of friction. That's what a single molecule would experience, and that's not what an ensemble of molecules would experience. But nevertheless, we wanted to see what the result of this type of molecular-like friction would be on the rheology of the system, and we compare with some molecular dynamics, and as you can see, the actual result was pretty much consistent. So basically what we did, we changed the amplitude of this gamma factor in order to study how the fluid would slip through this configuration. And as I said before, the job of lattice Boltzmann is to take from the small scale up to the device. And that's what we did. So what I'm dreaming of, Lydéric, is we know about QMMM, quantum mechanics, which was pretty successful, by the way. I'm dreaming of quantum nano to meso macro, where actually Keldysh would take care of the quantum nano, the basic physics. There must be some handshaking region, but we can push lattice Boltzmann pretty much down as long as we can coarse grain sensibly. We call this extended universality. Extended universality means that you don't know whether you are dealing with oxygen, neon, argon, but you have to formulate your problem in terms of dimensionless number. Extended means that the number of dimensional groups could be 2, 3, but still these are dimensionless numbers. If this is the case, lattice Boltzmann should be working properly. So if this interface is not empty, then we can import the Keldysh information and take it all the way to the device scale. I don't know whether this is daydreaming. I hope we can discuss that in much more detail, but that's exactly what I would like to do as not conclusion, I mean, as a startup of a new phase after this workshop. And with that, I'm done. Thank you for your attention.